There's an order to code, right? There's always a thread of execution. And typically, this is explicit. This is something that is evident from the code. But when we're dealing with events, this isn't there for free, right? We have to articulate the relationships between these events. We have to articulate what ties these together. And that's not to say that everything is tied together into a single thread, but the process of event-driven programming is the process of describing relationships between these discrete, loosely coupled, loosely ordered events. But what about the inverse, where we take this structured execution and we turn it into these loosely coupled, loosely ordered, discrete events? That's logging. And if you look at it this way, it's interesting and important to think about what we lose in this process, right? We have this connective tissue that holds these things together. We have this narrative. And when we go into logging, when we create this log stream, we lose that. We lose the narrative. We have instead all of these individual little things that are happening. And the result of this is that when we are looking at what happened, we're going over our logs because something went wrong, we have to piece this together, right? We become archaeologists. We have to figure out what underlies this collection of statements. And this might not seem like such a big deal because we wrote the code, right? We understand, at least mostly, what the relationship is between what's happening and what's getting logged. But consider that we're not looking at just the output of one process, right? We're looking at the merged output of all these things that are going on at the same time. And this is less clear. This is less something that we can extrapolate from our understanding of our code, because we may understand any of these individual threads in isolation, but we don't necessarily understand what their combined output looks like. And so when we talk about logging, we have to acknowledge that it's a lossy stream of data, right? If we don't capture context in what we log, it's gone. We don't have it anymore. And as a result, we tend to log a lot. We tend to create this enormous verbose stream of stuff because we don't know what we need. We don't know what we're going to need to refer to in the future. But this presents a different problem. It makes it so that everything kind of obscures the one thing that we're looking at. We have this enormous collection of data that we have to pour through, and we end up having these little notes about what patterns to grep for, to look for in our logs. And this is okay, but it's not great. At the same time, we can't really live without logging, right? It has these problems, it has these warts, but what logging gives us is a way to gain insight into our code without affecting how the code works, right? We have this stream of data which exists outside of the flow of our code. And we get this from print lines, we get this from log statements, we get this from a variety of different sources, and we can't live without it. Lamina is a library that deals with streams of data. It allows us to transform and aggregate data, to focus in on facets, to take many events and turn them into one. It allows us to analyze data, to find patterns in them. And allows us to react to data. It allows us to take these things that we discover from the stream of data and fold it back, to change how we filter the data, to change how even the code itself executes. But the thing that I want to focus on in this talk is that Lamina allows us to regain the narrative. It allows us to tell a story based on these collections of loosely connected events. And so when we talk about events, it's important to realize that there are actually two pieces of data. There's what the event contains, the actual data, but also when the event occurs. And in Lamina, this has a first-class representation, which would typically be called a future or a promise, but those were taken. And so there's called the slightly less elegant async result. More interesting is a first-class representation of a stream of events, which is to say a collection of events that may occur at some point in the future. And this is called a channel. And a channel is actually two parts. It is a node which takes messages, optionally transforms or filters them, and propagates them downstream. and a queue, which accumulates message when there is nothing else downstream. And so if we take a channel and we enqueue a message into it, it will pass through. This is just an identity node, and it ends up in the queue. But if we map a function over it, what we actually do here is we modify the topology of this directed graph. We add a node downstream of our original channel, and this is something that will transform all messages that flow through it. It takes messages from the queue of the upstream channel, and they pass through, and now we have two sitting in the queue of our second channel. And we can enqueue more messages, and this will pass through and be incremented and end up in the queue. We can have multiple transforms applied to the same channel. And again, this is fine. This is just a directed graph. And if we pass in another message, it will get split. And because in Clojure we have pervasive immutable data, this is fine. This is safe. It's worth noting that these diagrams that I'm showing you here are actually part of the library using GraphViz. And in addition to making it much easier for me to put together this presentation, this actually is a really powerful tool, because what you're doing by applying these operations to these channels is you are incrementally building a topology. And it's hard to figure out what that topology actually looks like, right? This is just a bunch of code like independently operating on pieces of your graph. And to be able to see that in its totality is very useful. I speak from experience. This is a very, very useful tool. We can also combine the output of channels together. If we have three channels, A, B, and C, and we join A and B to C, C is now a representation of the combined output of those two channels. And you may be wondering, what do we do with these messages, right? Well, we can read them out one by one from the queue. But we can also simply just register a permanent callback and say, every time we get a message, I want to do this. In this case, I want to print it out. We can also close channels. And the reason for this is because we don't want to simply just continually add to this topology. We want to be able to say that we don't care about something anymore. We want to be able to not have this just sit around forever. And if we close A, it's worth thinking about what happens then. Based on what I've told you so far, you would expect that there would be a queue for the incrementing node, and messages would just accumulate there. But that's not really what we want. What we want is to take into account the fact that this node exists to put messages into this thing that we just closed. And so what happens by default is that if we close the only node which is downstream of another node, that back propagates and continues back until it reaches something that still has something downstream of it. And so the net effect of closing A is this. So we have map, which I showed you. We also have filter. We also have a number of other very familiar functions followed by a star. And you may be wondering, what's the point, right? I mean, I've shown you something which has a different underlying implementation, but what does this give us that Seeks don't already give us, right? Is this just being different to be contrary? And the answer to that lies in reminding you that an event is data and time. It's the time that the event occurs. And something that we don't get from a lazy seek is an understanding of when that data became available. We know when we consumed it, but we don't know when that event actually came into being. And so there are a lot of other functions in Lamina which are less familiar. We have sample every, which at a fixed interval will emit the most recent message that it saw. There is partition every, which at fixed intervals will emit a list of all messages that it's seen. There's a function that will give you the rate of messages passing through it, a function that will give you the mean value of numbers passing through it. There's periodically, which will, at set intervals, evaluate a function and emit them. And finally, there's combined lattice, which takes n many channels, a function with n arguments, and every time a message is emitted from one of those channels, we'll reevaluate that function with the last n messages and emit that. So that's proper spreadsheet-style data flow. And we can implement this using seeks, but we have to make the seeks eager. And this costs a thread, right? We have to have a thread which is as fast as it can realizing elements from these sequences. And something to realize is that if we have something like combined latest, which is taking messages from multiple sources, we're having one thread per edge, right? We have to have something which is actively consuming all inputs. And there's been a lot that's been said about threads, maybe largely in conjunction with Node.js, and I want to state for the record that threads aren't bad, right? There's nothing inherently incompatible with threads and events or anything like that. But at the same time, there's a cost associated with this. What's maybe a little bit more intractable is if you consider the backpropagation mechanism that I just described, consider where we're doing this with these eager threads, right? Each of these operators here have these threads which are actively pulling from what's upstream. And because these are separate processes, because there's no real communication, they have these queues. And each of these processes do not know whether there's anything downstream of it, right? There's no way for a consumer to communicate, hey, I don't care anymore. They can ask for the next message, but that's it. And so if we decide that we no longer want to log the mean rate of messages flowing through here, this will just accumulate forever, unless we have some representation of this topology, unless we have something that sits above this seek abstraction. And so, again, that's completely doable. It's not really a problem, but the point is that we're kind of tending towards this mechanism that I've already described. And so Lamina has a niche. It has something that it does well. It's good at dealing with temporal streams of data, data where we care about when an event occurs. It's good at dealing with granular streams of data because the incremental cost of having a complex topology is quite low. And it's good for reasoning about streams of data because this topology is explicit. It's something that we can examine. It's something that we can walk. Whereas when you're looking at a bunch of operators on a sequence, typically the only time that we ever see that is in a stack trace, right? You have the rest, or first, or whatever that kind of, goes up the stack, but there's no real way for us to introspect on that. So the question is, how do we apply this to logging? And so there's a special construct in Lamina called a probe channel. And a probe channel is grounded, which means that messages will not accumulate in this queue. They are permanent, which means that they cannot be closed. And they are named, which is to say that there is a namespace for these. If we talk about probe channel ABC, that is the same thing wherever we go. To put a message into a probe channel, we use a trace macro. And the trace macro takes a name, in this case, foo::bar, and has a body, which will return an expression. And if and only if there is something currently consuming a probe channel, will this body be evaluated? The cost of having a trace statement for something which we do not currently care about is effectively nil. To consume the data, we can either take an individual probe channel, and by convention, these are colon delimited. So in this case, both of these statements would return the same thing, because if we're given a sequence, it will simply join them by colons. We can also select the combined output of multiple probes by passing in one or more either patterns, which are wildcard strings, or a full-on regex. So in this case, we would have a channel which represents these three things. And so it's worth taking a moment to look at what this gives us, right? This is not particularly complicated or anything like this, but what this allows us to have is our own custom log levels, right? You're familiar with whether or not you want to see info or something like that, but this doesn't really closely map onto our application semantics. This is meant to be the lowest common denominator. And if we're able to have something more descriptive than that, and we're able to collect the combined output of that, then we're able to look at subsets of the data flowing from our system, from the execution of our code, in ways that we could not before. However, it's also worth noting that even though logging doesn't change the semantics of our code, it does make it less readable often, right? If we have these trace statements everywhere, that affects our ability to understand what's going on because these things are just kind of sitting together. And so, based on the fact that most of the time, an interesting event coincides with when a function is invoked, we're able to create implicit probes that happen every time a function is invoked. And in this case, we take the addition operator, and we instrument it. And this will return a modified function, which, when it is called, will emit particular pieces of data when the function is invoked, when it returns, and when it throws an exception. And the first one, the enter probe, notice that it is namespaced underneath plus, which is the name, will give you 3 pieces of data. It will give you the name of the function, it will give you the timestamp, and it will give you the arguments. When the function returns, it will give you those same pieces of data. It will also tell you how long it took in nanoseconds, and it will give you the return value. There are also some other fields that I'll talk about in just a second. The error probe will give you pretty much the same thing, except it will give you an exception in the place of the return value. So there's a definite instrumented macro, and by default, the name associated with this will be the namespace colon the name. And we can also, using the function metadata, give an explicit name. And notice that these are 2 instrumented functions, and that one is calling the other. So if we consume the return probe for the parent function, the function which is calling the other function, we get this. In addition to all the other data about the return value, about the duration, this implicitly captures the return data for the instrumented functions that were called within that scope. And the reason for this is that this is a relationship that we want to hold on to. It's a relationship that we want to capture, right? This is part of our narrative. And because we get to choose which functions get called, we get to be selective in terms of what we're capturing. We get to focus on the important parts of our code. It's worth noting that you can configure whether or not you want to have functions implicitly captured. You can configure whether or not you want to capture the input or the return value. But by default, this is a useful thing. This is a new thing, because we can look at, for instance, why at a top level our web requests are taking a really long time, right? This happens. We have these little outliers, these blips. And this may be because deep down in the stack, we're making a horrendously inefficient SQL call. We're doing something unusual. To be able to correlate the top-level behavior with this internal behavior is something that we would have to work at by default in a typical case, because these 2 statements, that this call was made and this function took a long time, are not connected in any sort of obvious way. Maybe they share a thread ID or something like that, but it's not something that we have easy access to. It's something that we have to infer. This also has a nice benefit of giving us a slightly more useful time macro, which will tell us not only how long the overall body took, but also how long was taken by all the internal functions. So you may be wondering, what are you giving up by instrumenting your functions? And if you're not consuming the data, then the performance difference is equivalent to adding together 2 numbers and using apply to add together a list of 2 numbers, which is to say, it's not nothing, this isn't magic, but for the most part, you don't care. If you don't really think very hard about whether or not using apply is the performant thing to do in a situation, then this probably doesn't matter. If you are consuming the data, we have to actually construct the timing data structure, and that takes a little bit longer, on the order of about a microsecond, which is to say, again, you don't want to use it everywhere. You want to be selective in terms of where you use it. But if what you're doing is not computationally trivial, or you're doing any sort of I/O, this fades into the background. It doesn't matter. Thread pools are interesting because we have this conceit, we have this idea that all the different things that are going on in our program, because we are functionally pure, because we don't have side effects, we can reason about them in isolation. And this is largely true, except that there are certain fixed resources, right? We don't necessarily want to have 1 thread per request. And so we have a thread pool. And all of a sudden, these things which we consider to be separate, these things which we are reasoning about in isolation, they come together, right? And now all of a sudden, we can't really think about them in isolation, not completely. This is not something that is a perfect abstraction. It becomes lossy. And it's really actually quite hard to tell what's going on inside a thread pool, right? If you start to have things back up, like things are taking longer, right? It's taking a long time for these things to complete. You suspect that something's backing up somewhere. You might look at the queue size and say, looks like something's wrong. But this is, we're looking at sort of external phenomena, which is kind of adjacent to the actual execution of our code. And so Lambda provides an executor, which is a slightly overused noun, but it's an instrumented thread pool. It's something which works within this framework, this instrumentation framework. And so an executor is pretty simple. You create this by giving it a name, giving it some stuff about maximum threads, minimum threads, timeouts, other stuff like that. And once you do that, you can take an instrumented function and say that it uses this executor, which is to say that when this function is called, its execution is deferred onto this thread pool. And this will return something akin to a future, right? Something that you can dereference or use in other sorts of ways. And the value emitted by the return probe will now tell you how long was this in queue, right? Not just how long did it take to compute, but how long did it wait to be executed. And we can consume this from two different places. We can consume this from the return probe for a function. We can also consume this from the probe channel associated with the executor. And this is interesting because, typically speaking, we have more than one function using a thread pool. And these functions, because they share the same thread pool, they're related, right? We can't necessarily safely reason about them in isolation. But what the executor probe channel gives us is a view of how these things are related, how these things are coexisting with each other. This is something that we didn't have before. So there are a variety of functions that Lambda provides to do statistical analysis of things. And I'll talk about a few of them here. Mean gives us an exponentially weighted moving average, which is to say that as the data is going through, we are able to look at what is the average over the last window, the last 5 minutes, the last 30 minutes. And the reason why it's useful to have this be configurable is because if these two things are different, right? If the moving average over the last hour is different than the average over the last 5 minutes, this means something's happening now which is unusual, which is interesting. And we can use this to look at the output of our thread pool, to look at what is the average in queue duration, which is to say how long are things waiting on average. We can consume this, we can look at exactly what's going on. And this is a dimension of data that we didn't have before, right? This is novel. We can also do quantiles. We can get the statistical distribution of data, which is to say that, you know, the mean on average is the average. It's the 50th percentile. We can use that, but we also might be interested in what's the 90th percentile, the 99.9th percentile, right? If we're having a few little outliers in our data, that will register as a tiniest of blips on our mean. But to see that we're having these things which are taking orders of magnitude longer than our average, that's something that we want to know. And so we can look at, for instance, how often is a function being called. So we can simply just get the rate, we can get the statistical distribution, and this means at fixed intervals, if we have an uniform distribution between 1 time a second and 10 times a second, we'll get this, which is a mapping of the percentile onto the rate. An interesting one is outliers. So we can do this moving average, right? We can also get the variance. And because we can compute these things, we can actually determine, by looking at this data, how interesting is this? How unusual is this? And this is something that we can fold back into our actual data processing. And if we have something like the return probe data, which is big, right? It's not something that we want to log all the time. It's not something that we necessarily care about. We can filter out only the ones which are unusual. We can look at what is the mean duration and what is the variance. And we can say, I only care about things which are 3 standard deviations away. And we should only let those through. And this is interesting, right? This is actually kind of cool. But what's really interesting about this is what this represents. Statistical insight into a system is typically outside of the purview of the process. I don't know if you guys use like StatsD or Graphite or these other sorts of things, but that is outside our reach once we put it there within our process. You know, we as engineers can examine it. We can try to figure this out. We can see that something's going wrong and then try to swim back upstream and figure out what's going on. But this is not something which coexists. This is not something which we can fold back into how we're dealing with things. And so, you know, outliers is interesting. It's neat. It might actually be useful if you want to look at unusual things. You want to identify stuff that doesn't look like everything else. If you want to look at the rate of outliers to see if maybe you've spiked and hit some sort of weird situation. But I want to focus on really that this is a class of capability that you wouldn't really have otherwise, because we are able to have first-class data being emitted by these operators, which we can use within Clojure, which we can use within our process. We are able to change how our process is analyzing it, potentially even how our process is running. And this is not something that we want to do all the time, but the ability to do it is valuable. And that was the slide I was meant to be on. So far I have talked about how to merge together many streams, right? We can be very, very granular in terms of the probes that we define. We can join them all together. I can look at the return probes from every single function. I can look at the combined error rate of all the functions, all this other sort of stuff. But consider a ring handler, right? This is a single function which represents every single web request that comes in. And let's say that I want to know how often things are getting called. I don't want to know how many requests per second I'm getting. I want to know for a given URI, for a given request type, how often is this getting called? Because, you know, we might have some very cheap calls, we might have some very expensive calls. To group them all together doesn't really get at the heart of what I want to know. It's a piece of data. It's not really the most useful piece of data. And so distributor is something that takes a stream of data, looks at a facet of that data, and splits them off by facet into a bunch of parallel channels, which all have the same identical operation applied to them. So consider the ring handler, right? We're getting a stream of these requests coming in. And every time that we see a new URI, a function is called. It says, here's a new channel. Please do something to it. In this case, we are calculating the rate, and we're putting it together as a tuple of the URI and the rate. And you'll notice close on idle. And the reason for this is that we are creating lots of channels. And if the URIs on our system are not bounded, then we will, without bound, create these channels. And that's a leak. And we don't necessarily want that. And so this says if you don't get any messages within 10 seconds, close yourself. And this is fine. The next time that we get a URI that matches that, we'll just recreate it, and that'll work just fine. But if we get 3 requests, and they are to the root, and to ABC, and to DEF, then this is what the topology then looks like, right? The distributor is splitting these off, and it's applying these identical operations to it. And at the end, we have these queues, which contain these 3 tuples, right? Which is the URI and the rate. And so the question is now, what do we do with this, right? We don't really want to have just all these little streams of tuples. These are not things that are a really great representation. We want a mapping of these URIs onto the rate. And so aggregate does that. It takes periodic streams, which is say streams that emit at a fixed rate, and many streams which emit at the same fixed rate, and it merges all those messages together. And so in this case, the facet that we want to merge on is the first element of the tuple, the URI. And we get this, right? And these are the 3 individual messages. And notice that we haven't specified what the interval is. In this case, it's a second, because we're getting it the rate per second. But we don't need to know that. All we need to know is that because these are all emitting at the same rate, the first time that we see a duplicate URI, we've hit our period, right? We have looped over all the data that we're going to see. And so then this gets bundled up into a mapping of the URI onto the data that we saw. And downstream, we can clean up the values such that it's only the rate. And there we go. And these are useful in isolation, distribute and aggregate. But really, mostly, they're going to be used in conjunction with each other. And so, unsurprisingly, there's a distribute aggregate function which does exactly this. And if we apply this to that same stream, it will, at fixed intervals, emit this, what you'd expect, a mapping of the URIs onto the rates. And what we can do now, right? We have all these data that have all these facets, right? For instance, we have an executor probe, which is emitting every time a function returns. Every time it evaluates a function, it's emitting a bunch of data. It's emitting what the function's name is, what the duration is, all these other sorts of things. And maybe we want to know what function is hogging our CPU here, right? We can say, oh, well, the combined wall time that's being used on this sort of stuff, and we just merge it all together. But we want to get granular. We want to look at the data from a particular facet. We want to split it along this particular line and see what's going on. And what this does is, by splitting on the name of the function, we then map over the duration, we sum it together, and now at a fixed interval, what we're going to be getting is a map of a function name onto the number of combined nanoseconds that took up. So now what we get is we get this really fabulously new view into our system. We get this understanding of how are all these things interacting. Is this relative to this taking up a lot of time? Is it starving out the other sorts of things? Aleph is a library which uses Lamina to represent network communication. It uses the channels to represent network communication. And I named Aleph after one of my favorite stories, which is by Jorge Luis Borges. And it's about this guy that discovers that if you go down 17 steps into a wine cellar and look up at just the right angle, you see a point that shows you everything at once, right? It is the only place on Earth where all places are. And I call it this because I like the story. I thought it was a cool name. The library doesn't really quite live up to it. But what I've come to realize is that a networking library is about shuffling lots of data. It's these consistent, continual, concurrent, repeating processes. And something which just allows you to shuttle data around without giving you insight into how that's happening, into how all these processes are coexisting and how they're interacting with each other, is really only half of the library, right? The instrumentation and the ability to move data around are not separate libraries. They're two sides of the same coin. And by this measure, Aleph has been basically half of a library. But this is something that I'm working on. It's a work in progress. One of the things that I've added in recently is, by convention, everything that talks over the network, when it sends a packet, will emit via a probe the name of the thing, the HTTP server, the client, the thing that's talking to Redis, whatever, the remote address that it's talking to or receiving packets from, and the number of bytes. And simply because we have this by convention, right, that all these kind of disparate pieces, all these different sorts of things, there's these things that can make HTTP requests, these things that can be a TCP server, all these other things here that they just have agreed by convention to emit this piece of data. We can, for instance, say, what is the bandwidth being used by each of these elements in our system every second? We split on the name, we map over the number of bytes, we sum it together, and we select from everything on traffic : out. And now all of a sudden, at a very high level, we have brought together this one fact, which is, here is the bandwidth being consumed across our entire process. If we want to look at the other facet, which is the remote address, right? What remote address is consuming a lot of bandwidth? We can do the same thing with the added thing that we have, the close on idle mechanism, because the number of remote addresses we're talking to is probably not bounded. But again, I mean, this may seem kind of like, yeah, I could put this together too if I really wanted to, but the point is that we've simply agreed that when something happens, we emit some context, some information about what's going on here. And if we choose to care about that, we can combine that. We can align this data along any dimension that we want. And we can understand something new, something that wasn't really trivial to get at before. And it is fairly trivial to instrument or code in this way. And so those are the examples that I have. These are primitives that I've shown you, right? There is no killer app here yet. And so what's missing are a few things. One is that there are better examples in this. These are examples that I could explain to you in a short amount of time. There are, I think, more compelling ones that can be found. Process aggregation is a big one, right? Right now what you can do is you can consume within a process, but this is something that you actually have to set up ahead of time. When you boot up your process, it will hook into these probes and it will either consume it or not consume it. This is something you could almost figure out at compile time. What's more interesting, and is something that we've used at Runa in some respects, I've written prototypes of this, is the ability to, across your entire system, tap in to some stream of data that you didn't really care about. You don't, it's too wordy, it's too verbose, it's something that you don't care about in most cases. In our case, it was the full request response cycle for a fairly verbose XML service. But when we do care about that, when we want to track it for a very particular person, when you want to say, when somebody calls with this particular cookie, for this particular merchant, tell me what they're seeing. And you can do that. You can reach in and you can pull that one very granular stream of data down. And this is something that you would either have to temporarily raise the verbosity of the logs and then grep for, or I don't even know what you would have to do here. But this is a brand new capability. This is something where all of a sudden you can, across your entire system, start to pull together pieces of information. And then the question becomes, what do you do with it, right? There is, where do we put this data? Do we put it into Graphite? Do we create visualizations? Do we have some sort of web front end for this? And the answer is I'm not sure. I have some ideas. I plan to be working on them, and I don't know. I hope that, to some extent, despite the rather sweltering heat and everything here, that, you guys have, I've communicated the possibility here, right, the potential here. And I think that this is something that could be very interesting for people doing all sorts of development in Clojure. And if, you share my opinion on that, I would really love to talk to you and work with you at kind of exploring the possibilities here. And that's it. Thank you. No questions? Yes?
Are there any parallels or uses for this newfangled reducers framework?
The question was there any parallels or uses for the reducers framework? The reducers framework relies on all the data being available, and this does not. And so, no, they probably won't be working together. Yes? So, okay, let me try to understand. You're asking, I mean, so to be clear, this is not interfering with the stack trace being thrown, right? It's capturing that there was an exception, but it's not swallowing it or anything like that. Yes. And so, I mean, you could be capturing this and you could be throwing out this stuff, or you could be looking for an elevated error rate or something along those lines to increase the level of logging or the whatever. Like, you're looking for probably sort of collective conditions that will cause that, because, I mean, depending on how significant an exception is in your code, you may not want to be collecting, like storing in memory, everything that's going on everywhere just in case an exception is thrown. I mean, that's possible, but maybe not the most desirable thing. Does that answer you? Okay, yes? Mm-hmm. In like the elevated error rate sort of thing, like this is something that I have experimented with, and the outlier thing is an example of how this could be used. I haven't found something where I'm like, oh, holy hell, I have to tell the world about this. Like this is, like I said, these are primitives, these are novel capabilities. I have, maybe unwarranted faith that they will be useful depending on certain situations, and because they are things that you can map very closely onto your application semantics, I think that, people can find uses for them, but I mean, that remains to be seen. Yes?
So, in having built similar systems in the past, one of the challenges I find is whenever you build an automated system that captures the arguments or return, you trip over the fact that some functions have very, very large arguments.
Yes.
Do you have a scheme for managing that?
Yeah, so I mean, I mentioned this in passing, but like you can configure which gets captured, whether you capture the input and output, either or neither, depending on whether or not this is something that you actually care about. To capture it, as in to distill it down to something that's a little bit more manageable?
So in large systems with very large inputs that we actually did need to capture and manage in memory, we would capture to global storage.
So, I mean, I think I'm understanding you. I mean, it's quite possible to immediately capture and write to some sort of durable storage. It's not like sticking around. Presumably, if you're able to capture it at all, it's in memory at some point, right? Or am I not understanding your question? So yeah, this is something that I didn't really talk. It's synchronous to walk across these. There is no like message passing or anything that goes along this. once a message hits the topology, it will go all the way to the leaf nodes synchronously, unless there's some sort of periodic like aggregation process, but you would have to actually put that in there yourself. Yes?
What's the domain to which we can pay? If there's a selecting thing to be progress, what's the using this as
So I work at Runa, and we have a fairly generic web service that goes through some logic, makes some responses as whether or not people should get offers on products that they're currently viewing. We're not doing any high-level streaming of data or anything like this, and so the domain in which I've been using this is to gain insight into why things are breaking, and understanding like the dynamics and like what is the sort of breaking point on some of these pieces of our infrastructure. And the thing that I want to mention here is that Aleph is an event-driven framework for communication. This doesn't have to be used in that context, right? You can use this with completely vanilla ring anything. This is saying that synchronous code can be seen as an event stream. And so, maybe I've said this too many times, but like this can be used in a wide variety of cases. That is the entire point. This can be applied to basically anywhere where we're calling functions and we want to have a sort of higher level insight into what's going on here as opposed to just a bunch of discrete little this happened and this happened and this happened. Yes? I mean, so, in as much as these are channels of data, you can pipe it into pretty much anything, right? I mean, so I have a, unreleased sort of alpha quality AMQP binding that will take these channels and literally you can just pipe it in. This is, again, one of those little things. This is when I was talking about data endpoints. That's one of them, right?
Last one?
Yes.
How high is, in your opinion, the risk of getting memory leaks or stuff like that gets things out of control? I don't know. Many URIs, too many remote addresses asking.
So as I said, I mean, this is something that you need to be careful of because, if it's an unbounded thing, then you need to make sure that you're closing it on idleness, right? And I mean, the memory cost associated with these topologies is tiny, right? Really, really small. And so you can have millions of nodes in these graphs, and this is not going to even, I think, register on, what you're looking at, assuming that you have this sort of non-trivial service that would require millions of nodes. And so I don't think that it's a big deal as long as you don't let it grow without bound, right? You have these sort of idle closed things. It's, I think, extremely unlikely that it would get out ahead of you and like you will like worry about whether or not you're being aggressive enough about closing it or something like that. And thank you.
Thank you again.